As usually happens, the discovery of electrons led to more questions. Doing scientific research is a little bit like an ant climbing up a tree. And you come up and there's these different branches, and you go off on this one branch, and then it subdivides into more branches and leaves, and there's just an endless amount of stuff to explore. And if you come to the end of one leaf, you just go back a little bit and go off in another direction. So there's negative electrons in an atom. We know that the overall atom is neutral, so there must be some positive charge in there. How do these opposite charges fit together? How are they arranged? Are atoms a jumble of more fundamental particles? If there's an electron in there, maybe there's some other particles in there as well. Are atoms solid spheres, or what exactly are they? Do they have internal structure? Lots and lots of questions. So Thomson came up with what's called the plum pudding model. Now, in the United States, we don't eat plum pudding. We don't even use the word pudding in the same way that they use it in Great Britain. The closest thing we have is probably a blueberry muffin. So think of this as being like a blueberry muffin where this sphere of positive charge, the red part, is the muffin, and the electrons are the blueberries, and they're just kind of randomly distributed. So, okay, you have to start somewhere. So it's like, well, maybe this is what it is. Okay, so it's called the plum pudding model. Then you test it, right? You don't just guess at stuff. Okay, so before we can talk about how it was tested, we have to talk a little bit about radioactivity. Radioactivity is the emission of small energetic particles from the core of particular unstable nuclei. It was discovered at the end of the 19th century by Henri, Becquerel, and Marie Curie. You've probably heard of her, famous female scientist. Radioactivity is very useful. It helps us to probe the structure of atoms. There are 3 types we're going to mention now: alpha particles, beta particles, and gamma rays. The alpha particles have a positive charge, and they are the most massive of these 3 different types of radiation. If you want to read more about radioactivity in your textbook, it's in chapter 20, possibly 21. I might not have updated that. So, 1909, Ernest Rutherford, who was one of Thomson's students, he believed in this plum pudding model. I mean, you're not going to go against your boss, right? So he's doing an experiment to confirm this model. So he takes a stream of positively charged alpha particles and directs them at a very, very thin sheet of gold foil. And the plum pudding model predicts that those particles would just go straight through the foil. They would just go through the bready part of this blueberry muffin thing. So here's the setup. Here's the source of the alpha particles, and here's the thin gold foil, and then they've got this detector around here so that they can see where those alpha particles went. And so most of the particles did go through, maybe got deflected a little bit, but most of them went through. Some of them were deflected at a significant angle, but what was shocking is that some of them bounced back. That was just like, what the heck is going on? So most of them went through, but about 1 in 20,000 bounced back. And Rutherford said this was about as credible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. So a piece of tissue paper, like in a gift bag, right? A 15-inch, think cannonball, shot from a cannon into the tissue paper, and it bounces back and hits you. Would you be surprised? Yes, you might be dead too, but you'd be very surprised, right? Because that shouldn't be able to happen. And that's how shocking this was. And so obviously the plum pudding model needed some work. So Rutherford came up with a new model to explain what happened in this experiment. This is what they expected to happen, that these guys would just go through, because these electrons are teeny tiny. Just go through, but what they actually saw was that some of them got deflected and some of them bounced back. So he concluded that matter must not be as uniform as previously thought. There must be regions of empty space and small regions of very dense matter. and that these particles, the alpha particles that bounced back, did so because they hit something much more solid than what was around them. It's a little bit like shooting airsoft pellets at a volleyball net. The volleyball net has these big open squares in it, right? Because it just needs to stop a volleyball, right? But an airsoft pellet from a gun would go straight through those, unless it hit a string directly, and then it would kind of bounce back, right? So this nucleus here is like the solid string in a volleyball net. And so this is the nuclear model. He called this the nucleus. Inside the nucleus, we have protons and neutrons, and outside the nucleus are the electrons doing something. So the nuclear theory of the atom, 3 basic ideas. Most of the atom's mass and all of its positive charge are contained in a small core called the nucleus. Most of the volume of the atom is empty space through which the tiny negatively charged electrons are dispersed. And there are as many negatively charged electrons outside the nucleus as there are positively charged particles inside the nucleus. Those positively charged particles are called protons. Protons are positive. They both start with P. So the atom is electrically neutral. So we've got positive charges in the nucleus, and we have an equal number of negatively charged electrons outside the nucleus. He's not saying anything about what those electrons are doing. So this model was very successful, but it was still incomplete. So they knew that a hydrogen atom had 1 proton, and a helium atom has 2 protons, and the mass of the electron is much, much smaller. And the hydrogen atom would have 1 electron, and the helium atom would have 4 electrons. And so you would expect that the mass of helium would be twice that of the mass of hydrogen. But it wasn't. Helium was 4 times heavier than hydrogen. There's got to be something else going on. So later work that Rutherford and one of his students did, Chadwick, demonstrated that that unaccounted for mass was due to neutrons. And these are neutral particles within the nucleus. So you can't really identify them based on, oh, well, here's the number of electrons, here's the number of protons, they're equal. But there's neutrons in there, and that makes up the extra mass that they couldn't account for. So the neutrons are neutral. Okay? Protons are positive, neutrons are neutral, no charge. The mass of the neutron is very similar to the mass of the proton. They are not exactly the same, but for our purposes, we can consider them to have the same mass. So the hydrogen atom has 1 proton and no neutrons. The helium atom, being 4 times as massive, has 4 times the mass because it has 2 protons and 2 neutrons. So that's a total of 4 massive particles compared to 1 massive particle for the hydrogen atom. So that nucleus is extremely dense, and extremely is an understatement. It contains over 99.9% of the mass of the atom, but occupies very little space. So if you think of a football field, standard football field, and on the center 50-yard line, you put a green pea. It's a regular pea that your mom made you eat, right? Maybe you've grown to like them, maybe not. You set that on the center, in the middle of the football field. Okay, that's the nucleus, the size of the nucleus. And then there's going to be electrons, and they're going to be just kind of around, and they're going to take up a volume that would be spherical in shape. But the distance from that nucleus to the edge of the atom would be the distance from the 50-yard line to the goal line on each side. A green pea in the middle, and this huge volume. And what's in there? A few things that are way smaller than the green pea. Matter is mostly empty space. It's kind of hard to get your mind around because, you know, you hit your head on the chalkboard. Feels pretty solid to me, right? Another way we can think about this is a cloud analogy. So electrons are a bit like water droplets in a cloud, or in fog, right? We all know what fog is. Those water droplets have negligible mass, but they're dispersed over a large volume. Clouds and atoms are both mostly empty space. So fog looks solid, right? You can't see through dense fog, but you can walk through it very easily. It's just little tiny droplets of water. It's actually mostly empty space, right? And that's the way that matter is as well. Why does it look solid? Well, it's because the variation in density is too small for our eyes to see. And so if we think about a scaffolding, or, I mean, this looks more like a jungle gym to me, the old-fashioned. They used to let us play on metal jungle gyms on top of asphalt. And we'd go out at recess and hang by our knees, upside down, no hands, over the asphalt. And occasionally we'd fall and land on our heads, and most people lived and nobody got sued. It was a different time. Anyway, ginormous jungle gym, right? If you think of the scaffolding being the size of a football field again, and 100 stories tall, right? That would be a massive jungle gym. That could be really fun. Standing down on the ground, you can see that that's mostly empty space. But if you flew over that in an airplane or a blimp and looked at it from outer space, anywhere you look, unless you're lined up just perfectly, you're going to see all of these different lines, and it's going to start to blur together and look like a solid object. And that's what happens with matter. When you knock your head on the blackboard, I don't recommend that. I might have a headache later. Or wrap your knuckle on the table. You know. It's like one giant scaffolding, your finger, crashing into another giant scaffolding, the table. So imagine two of these bumping into each other. They're not going to go through each other, right? And yet they are both mostly empty space. Yeah?
So in an atom, you have your nucleus, which is composed of protons and neutrons.
Mm-hmm.
And then between that and your electrons, it's just...
There's nothing. Yeah. So we're going to talk later in probably more detail than you want to know about what those electrons are doing. For now, we can just think of them as zinging around. And so they're taking up almost no space in terms of their actual volume, and yet they're sort of inflating this atom by their presence. It's a bit much to get your mind around. Any other questions?
So the density of the atom, does it vary from the nucleus?
Yeah, the density of the atom within the atom varies tremendously. Mm-hmm. The density of the nucleus is the most dense, and outside of that, there's almost no density. So the nucleus, if you were able to just put nuclei together, which you can't, but if you could, and make them the size of a period in your book, it would weigh millions of tons, because that's squeezing all the empty space out of the atoms, just taking the tiny, tiny nuclei. They are mind-bogglingly dense.
So when that experiment was performed with the reflection,
mm-hmm.
you were shooting it directly at the nucleus, or was that more like the...
That's a good question. So let's go back and look at that, the gold foil.
If there's no density in like that gray area, then shouldn't it have just...
Yeah, so there's no density in the gray area, and that's why most of the particles did go straight through.
The ones that happened to happen...
But the ones that just happened to either hit head-on a nucleus or get close enough to be glanced off, those would be deflected. And it was about 1 in 2,000 that actually hit the nucleus. You can't actually aim at a nucleus because it's too small. They're just shooting at this gold foil, which has lots and lots of different atoms in it. So there were lots of nuclei in there that could be hit. Yeah, good questions. But most of them went straight through because there's really nothing there.